Hey friends, it's Ben once again. This is a video for Calc 1. We are taking a look at limits. Previously, we looked at what I refer to as the basic limit laws, the ones that say, plug in your number and see what happens. If you recall, the basic rule I gave you last time was plug it in. If you don't get a division by zero error, you're done. So guess what we're going to talk about now? That's right, the division by zero error. So when this comes up, it doesn't mean you're done. Frequently, I have students who come to the exam never having figured out that 0 over 0 does not mean you're done. If you get 0 over 0, it probably means that there's a way to do algebra and turn it into something else, okay? So we're going to look at a bunch of examples, all of which end up with 0 over 0, or something else where there's a division by 0, and we're going to see what you should do in those cases. Now, this is not exhaustive, but it gives you all the kind of basic ideas of what we generally have to deal with on these, okay? All right, let me share my screen here, and we will get going with this. Screen mirror. Come on, iPad. Yay, it's going to work. Okay. So this one here, you can see that we have the limit is x goes to 8 of x cubed minus 64x divided by 8. Now, if you plug in the 8s there, you immediately see that you've got a 0 on the bottom. On the top, maybe that one is not quite as clear. That is because the number, see, 8 to the third power, in case you can't tell, I'm pulling up a calculator out to the side. You get 512 minus, guess what 64 times 8 is? 512. So when we have a 0 over 0, then we have algebra to do, okay? I'm going to take there and just erase that. And I need you to observe at every step, I continue to write limit as x goes to 8, okay? Then I'm going to factor the top. I can see that an x comes out of it easily. I'm left with x squared minus 64. And notice I don't do any cancellation at that point. A lot of times people want to come along here and say, x's cancel, haha. No, they don't, okay? If you want to do that cancellation, it has to be a cancellation of a factor across the whole top and across the whole bottom. And the thing is that division cancel, wow, that was a jerky line. So division cancels multiplication. So you have to have multiplication to cancel the division. Here we see that x minus 8 is going to cancel out. And you knew that that was the case, that there was going to be something to cancel because you got zeros on the top and the bottom. The only way that you ever get a 0 from a polynomial is if it has a factor that is x minus whatever it is you're plugging in, okay? Well, once we've got that, now our limit as x goes to 8 is just of x times x plus 8. There's no division left. So clearly we're not going to get a division by 0 error. So we will have 8 times, let's see, 8 plus 8 is 16. And so that'll be, I think it's 128. Boom, we're done. Okay. I'm going to say that a lot. Boom, we're done. I'm just indicating that when you get it to work, it's easy. But there's two kinds of math problems. The easy ones, those are the ones you know how to do, and the impossible ones, those are the ones that you're still working on. Okay, so we're going to have a lot of both of them. You know, our goal is to change one of them into the other. All right, so this one here, we've got the limit as x is going to 3, and you can see that when you take and plug that into the denominator, you're going to have 9 minus 9. That's clearly 0. But when you plug into the numerator, then the thing that you're getting is actually 6 over 0. It's not 0 over 0. Because it's not 0 over 0, it's not going to cancel. Okay. Now I have gone ahead and opened another app up here, Desmos. I know y'all did not get it installed onto your iPads. I'm looking to see if we can repair that, but for the time being, use Desmos on a laptop because you're going to be able to clip the pictures easier that way anyhow. So, all right, so we take a quick look at what's going on here. I cannot use my pointer on this, but y'all should be able to spot on here that the line we're really interested in is where x is equal to 3, because that's what we were plugging in. And I am going to take that and turn it into a dashed line so that you can see the asymptote better. Okay. So we have an asymptote, a vertical asymptote, and we're talking about x going to 3, not going to 3 from the left or going to 3 from the right. So when we jump back to our notes app here, we're going to jot down the limit as x goes to 3 from the left of x squared minus x over x squared minus 9. On the left-hand side, we got negative infinity. And the limit as x went to 3 from the right, that was the, the numbers that were bigger than x equals 3. We had it going upward to positive infinity. Since one-sided limits disagree, limit as x goes to 3, x squared minus x over x squared minus 9 does not exist. Okay, so the actual math I did there is pretty straightforward. We looked at a graph of it because we knew that we were doing division by 0, but it was not 0 over 0. We looked at a graph of it and we saw that we had it going up to positive infinity on one side, negative infinity on the other. If it had gone to the same infinities on either side, we would say that the limit is plus infinity or minus infinity, whichever it went to. But since this doesn't agree, we're going to say that our limit does not exist. Then the other thing is you need to notice I'm trying to teach you good writing habits. We say this limit here, the limit is x goes to 3 of x squared minus x over x squared minus 9, does not exist. We do not write lim does not exist. We do not write lim as x goes to 3 does not exist. If you had a teacher in high school who told you to do that, they were wrong. And I'm not being mean to your teacher, I'm just saying they were wrong. I have a PhD. Please trust me, you're supposed to write the whole thing, okay? If it's too much effort, sorry, it's what we do to write the whole thing, okay? All right, enough of me being mean. Let's look at this next one. It has a square root in it, and that's a little bit intimidating, okay? Just like before, we're going to plug in the 16. If you plug it into the denominator, immediately you see it's 0. The numerator is a little harder to figure out. You have to take a square root of 16, that's 4. 4 minus 4 is 0. So this is a 0 over 0, okay? If you have had calculus before and you're shouting, can't we just use L'Hopital's rule? No, we can't. L'Hopital's rule depends on derivatives. Derivatives depend on limits. You have to get the limit stuff first. If you're saying, I don't know what L'Hopital's rule is, good. Keep it that way, all right? We will get to it eventually, but just not yet. All right, so evaluating this limit, it is 0 over 0, but there's nothing to factor. So the way you're going to tackle this is to look at this piece with the square root. I'm going to put parentheses around this 2, but the piece with the square root is the important piece. It is something that we can conjugate. The conjugate of something that has a square root in it and a minus is the same thing replaced with a plus. The conjugate of something with a plus is the same thing replaced with a minus. So we're going to multiply the top and the bottom by the same thing. The reason that we do that is that when you multiply that top, it's a difference of squares, and it will turn into x minus 16. Square root of x squared will be x, and the square of 16 will be, square root of 4 will be 16. Now, here is something that is kind of a pro tip. See that denominator? Don't multiply it out. Everybody always wants to multiply it out, but if you, and that is usually because you had instructions to do that in high school or something. But here we do not want to multiply them out. See how this and this are the same thing? Sometimes you have to do some factoring before you spot that, but we get to cancel those two things out. We have the limit as x goes to 16 of 1 over the square root of x plus 4. Now, because we have a plus, we can just plug in, and we have 1 over 4 plus 4, so 1 over 8. And then we're done, okay? So that's the kind of thing that we're doing here. Spot them by seeing that you have this square root business here, and that it's associated with a 0 over 0 problem. You will have to multiply by a conjugate. The technical term for what we've just done here is referred to as rationalizing the numerator. You may have had an algebra class where you had to rationalize denominators, but here we're rationalizing a numerator. So, all right. So this next one has the same sort of thing going on. See how you have a square root of x minus 2 floating around in there? And when you plug in the 4, now we have a 1 over 0 minus, and you plug into the other one, you have a 4 over 0. So, I mean, your intuition is that that's going to be then 3 over 0, and so it'll be infinity. But is it plus infinity or is it minus infinity? So the trick on this is very similar. And we are going to take and rationalize that denominator. And we are not going to do anything to the other part. The reason that we don't do anything to the other part is that we will end up with the same denominator on these, and we don't want to goof that up. So the limit as x goes to 4. And notice that your numerator here is square root of x plus 2 divided by, on the bottom, you do want to multiply that out. It's a difference of squares, and you get x minus 4. Okay, so that means that we now have the limit as x goes to 4 of, since they've got the same denominator, we can put them together, and we end up with a square root of x, and then plus 2 minus 4 is a minus 2, and then we have x minus 4. And now, when you plug in the 4, oh no, it's 0 over 0, but you already handled this sort of thing in a previous problem. So we are going to do the same thing as we did before, rationalizing the numerator. And we will have a limit as x goes to 4. And our denominator has this x minus 4 and this square root of x plus 2. Did y'all notice that I did not multiply those out? But here in the numerator, I end up with just an x minus 4. Cancellation happens. And now I can plug in my 4 and have 1 over 2 plus 2. So 1/4. Boom. Notice though, there's all kinds of details in what's going on here. A big detail is that I wrote lim every time until I got to right here. The reason I didn't write it in this step is that I was actually plugging in. Now x is no longer going to 4, it's already got there, okay? Other stuff is that I did not multiply this denominator out, but I did multiply this one out. It is a little bit tricky to spot when you need to do stuff and when you don't. It mostly comes from doing lots and lots of practice. So, all right. Here is a different one that looks intimidating for a completely different reason. Now we have exponentials. And exponentials are sometimes just hard to deal with. But the thing that you have to spot to get this one to work out is that when you have 2 to the t and you square it, you get 2 to the 2t. So that means that this thing is what we refer to as being a quadratic form. It's kind of like a quadratic, but it's got something extra added in there. So the thing that you are going to have to do first is to plug in your t equals 2. When you do that, on the bottom, you got 2 to the 2 minus 4 is 0. On the top, you will end up with 16 plus 4 minus 20. So that's 0. So it's going to be 0 over 0. Something's going to cancel. Now, if it's giving you a headache to deal with factoring a 2 to the t, you might think of this as u squared plus u minus 20, which you could factor into u plus 5 and u minus 4. What we've done is to just use a variable in there as a placeholder so that our heads did not explode. Keep in mind, head could explode is a terrible disease. It kills millions of people every year. It really does not. But now I'm going to write 2 to the t plus 5 because u was 2 to the t. And 2 to the t minus 4. And on the bottom, I still have my 2 to the t minus 4. And I'm going to cancel those. Now I no longer have a division problem. I just have a exponential there. And I can just plug in. 2 to the 2 is 4. 4 plus 5 is 9. And then we're done. Okay. So the only real hassle here was the factoring. Well, okay, this step here. Lots of times people just don't spot that. But it's going to happen over and over again. If I have a cosine squared and a cosine, figure that I probably am thinking about the cosine, being separated out and getting squared. So same thing with an exponential or a log or whatever function you're dealing with. So. All right, so here's one with some trig functions in it. And these trig functions we're dealing with, when we plug the 0 into them, have a problem. Cotangent of 0 is not defined, and cosecant of 0 is not defined, okay? So in effect, we have something that's kind of infinity over infinity or something, but it's not super clear what to do. However, after we've seen that we can't just plug in 0, then we're going to do something with trigonometry. Hopefully you remember that cotangent is really cosine divided by sine, and cosecant is 1 divided by sine. That means that you can rewrite this as sine times cosine over sine. That's just algebra. The cosines cancel, and now we have the limit as x goes to 0 of cosine x, and that's just 1. Now, you might have looked at the first step there and said, aha, we have infinity divided by infinity. When you divide something by itself, you get 1. Please don't fall into that trap, because if I'd instead had cotangent of 2x or cotangent squared of x, it would have changed the problem significantly. Okay. All right. I think this might be the last one here. Let me peek and see. Yep, this is the last one. Okay, so this one, when you plug in pi over 2, because secant is 1 over cosine, you're getting a 1 over 0. And for tangent, because that's sine over cosine, when you plug in pi over 2, you get 1 over 0 for that as well. So looking at it, you might say, aha, 1 over 0 minus 1 over 0, I'm just going to get 0. Maybe, maybe not. That thing I was saying about sometimes they cancel and sometimes they don't, depending on how stuff just pans out. But we can tackle this in a very similar way. So our theta is still going to go to pi over 2. And we're going to think about the secant as being 1 over cosine. The tangent as being sine over cosine. And like I said before, you get 1 over 0 out of those. But now we're going to say the limit as theta goes to pi over 2, and apparently I can't write, pi over 2 of 1 minus sine theta over cosine theta. And now you plug in and everything's fine, right? Oh no, you plugged in and you got 0 over 0. But we've handled some 0 over 0s before, so I think we can still do this. So what we're going to do is to rationalize, air quotes, rationalize that numerator by multiplying it by 1 plus sine theta. We have to do the same thing to the denominator, okay? So when we do that, and you should rightly be wondering why we're doing that. The reason we're doing that is that you can then have the difference of squares to work out there, and your numerator has 1 minus sine squared. To which you say, I didn't really want that. It didn't help me. I still have 0 over 0. What's going on? But 1 minus sine squared, there's a nice trig identity that we ought to all be familiar with that makes that into cosine squared theta. And remember what I said before about don't distribute out. So once we get to here, we can cancel one of those cosine thetas. And now our limit is going to be cosine theta divided by 1 plus sine theta. And now we're going to try just plugging in. The cosine of pi over 2 is just 0. And the sine of pi over 2 is just 1. So you have 0 over 2. So that's going to turn out to be 0. Okay. So the approach that we had, infinity minus infinity, turned out to get us 0 on this. But if I had had a 2 on one of those, 2 secant theta or 2 tangent theta, it still would have been infinity over infinity. And we wouldn't have gotten that nice cancellation. So anyway, I'm going to stop the share right there. So these problems all require you to know some of your basic trig identities and to be able to do just gobs and gobs of algebra. That's 80% of calculus is doing lots of algebra. So tricks to remember now: factoring, rationalize the numerator or rationalize the denominator. getting least common denominators to put things together nicely, and then being able to recognize things that are in quadratic form or otherwise stuff that have shown up in other classes previously. So, all right, so I will see you all in class. Make sure and ask any questions that you might have about this. I'll try to answer them at the beginning of class. All right, talk to y'all later.